Imagine a state where 60% of voters prefer the blue party and 40% prefer red. You'd expect blue to win most of the seats, right? But with the right map, you can draw district lines so that red wins every single seat, or blue wins every single seat. Same voters, same preferences, completely different outcomes. The only thing that changed was the lines on the map. This is gerrymandering, and for most of American history, courts have struggled with a maddening question. Everyone can feel when a map is unfair, but how do you prove it with mathematical rigor? Turns out, mathematicians have developed remarkable tools to do exactly that, and some of these tools have already changed the outcomes of real court cases. Let's start with the intuition. Picture a simple grid. 25 voters arranged 5 by 5. 15 are blue, 10 are red. That's our 60-40 split. Now we need to divide them into 5 districts of 5 voters each. Here's one way to draw the map. You group 3 blue voters with 2 red voters in each district. Blue wins every district 3-2. 5 seats out of 5 for a party with 60% support. That's disproportionate, but at least the majority party is winning. Now rearrange the lines. Pack all 15 blue voters into just 3 districts, 5 blue in each, and spread the 10 red voters across the remaining 2 districts. Now blue wins 3 seats and red wins 2. That actually seems proportional and fair. But here's the devious version. Crack the blue voters apart. Put 3 blue voters into each of 5 districts, but pair them with 2 red voters. Wait, that's the same as before. The real trick is to pack 5 blue voters into 1 district, then distribute the remaining 10 blue voters across 4 districts, with the red voters arranged, so each of those 4 districts has 3 red and 2 blue. Now red wins 4 out of 5 seats despite being only 40% of the electorate. The minority rules. Same voters. Different lines. Opposite outcome. So how do mathematicians formalize this? The first tool is called the efficiency gap, and it's elegantly simple. The key insight is that gerrymandering works through 2 tactics: packing and cracking. Packing means stuffing your opponent's voters into a few districts so they win those seats by huge margins. All those extra votes beyond what's needed to win are wasted. Cracking means spreading the remaining opposition voters across many districts so they lose everywhere by small margins. Those losing votes are also wasted. The efficiency gap counts these wasted votes for each party. A wasted vote is either a vote cast for the losing candidate in a district, or a vote cast for the winning candidate beyond the number needed to win. You compute total wasted votes for each party, take the difference, and divide by the total number of votes cast. If the result is 0, neither party is being systematically disadvantaged. If it's large, say above 7 or 8%, one party is wasting far more votes than the other, which is the mathematical fingerprint of gerrymandering. This metric was actually presented in the Supreme Court case Gill v. Whitford in 2018, involving Wisconsin's state assembly map. Researchers showed that Wisconsin's map had one of the largest and most durable efficiency gaps ever measured, consistently favoring Republicans even as the overall vote shifted. But the efficiency gap isn't perfect. It can be thrown off by uncontested races, and it makes assumptions about what a fair baseline should look like. So mathematicians developed additional tools. One family of measures focuses on shape, the geometric compactness of districts. The idea is simple. Gerrymandered districts tend to look bizarre. They snake along highways, sprout tentacles, or wrap around communities in ways that no reasonable person would draw. The Polsby-Popper Score quantifies this. Take the area of a district, divide by the area of a circle with the same perimeter, and multiply by 4 pi. A perfect circle scores 1. A long skinny snake scores close to 0. Another measure is the convex hole ratio. Compare the district's area to the smallest convex shape that contains it. A convex shape is one where you could stretch a rubber band around it and it would lie flat against every edge. The more the district deviates from its convex hole, the more it looks like someone drew it with ulterior motives. Compactness measures are intuitive and easy to compute, but they have a limitation. Geography isn't uniform. Rivers, mountains, and the shapes of states themselves impose constraints. A perfectly fair map might still have oddly shaped districts simply because the population lives in oddly shaped patterns. So compactness is suggestive, not conclusive. This brings us to the most powerful mathematical tool in the anti-gerrymandering arsenal, and it comes from an unexpected place: statistical physics. It's called Markov chain Monte Carlo, or MCMC. The idea is beautifully creative. Instead of arguing about what a fair map should look like, you generate thousands, or even hundreds of thousands, of alternative maps that satisfy all the legal requirements: equal population in each district, contiguous boundaries, compliance with the Voting Rights Act, reasonable compactness. You're not looking for the one perfect map. You're building an entire universe of legitimate maps to see what's normal. Here's how the Markov chain part works. You start with one valid map. Then you make a small random change, swap a precinct from one district to an adjacent district, and check whether the new map still satisfies all the constraints. If it does, you keep it. If not, you try again. Each small change is a step in the Markov chain. After thousands of steps, you've wandered to a completely different valid map. Repeat this process and you build an ensemble, a representative sample of the space of all possible legal maps. Now take each of these maps and simulate the election using actual vote data. You get a distribution of outcomes. How many seats would blue win across all these randomly generated fair maps? Maybe across 50,000 random maps, blue wins between 5 and 7 seats out of 13 in 95% of cases. Now look at the actual enacted map. If blue wins only 3 seats on the real map, way out in the tail of the distribution, that's a massive red flag. The map is a statistical outlier. It's producing results that virtually never occur by chance when lines are drawn without partisan intent. This is exactly what mathematician Jonathan Mattingly and his team did for North Carolina's congressional map. They generated over 24,000 alternative maps, satisfying all legal criteria, simulated elections on each one, and showed that North Carolina's enacted map was an extreme outlier, producing a 10-3 Republican advantage in a state where the ensemble of fair maps almost never produced such a lopsided result. Their work was presented as expert testimony in court, and in 2019, a state court struck down North Carolina's maps as unconstitutional partisan gerrymanders. Duke mathematician Moon Duchin founded a program called the Metric Geometry and Gerrymandering Group, training mathematicians to serve as expert witnesses. These aren't political activists, they're researchers who let the math speak, and the math has proven remarkably persuasive to judges who previously felt they had no objective standard to apply. But here's where we hit the fundamental tension, and it's important to be honest about it. Math can detect when a map is unusual. It can quantify the degree of partisan asymmetry. It can show that a map is a 1 in 1,000 outlier. What math cannot do, by itself, is tell us where to draw the line between acceptable and unacceptable. Is a map that falls at the 95th percentile gerrymandered? The 99th? Who decides? The Supreme Court, in Rucho v. Common Cause in 2019, ruled 5-4 that federal courts cannot adjudicate partisan gerrymandering claims, not because the math is wrong, but because the justices couldn't agree on a manageable standard for when partisan advantage becomes unconstitutional. The math works. The legal and political consensus does not. At least not yet. Still, the mathematical tools have found success in state courts operating under state constitutions, and they've fundamentally changed the conversation. We've gone from I know it when I see it to rigorous, reproducible, quantitative analysis. The efficiency gap gives us a single number. Compactness measures give us geometric evidence. And Markov chain Monte Carlo gives us the full context of what's possible, making outliers impossible to ignore. The math of gerrymandering sits at a beautiful intersection of geometry, probability, and civic responsibility. If you found this interesting and want to see more videos exploring the mathematics hidden inside everyday life, please hit subscribe and like this video. It genuinely helps the channel grow. And if you'd like to support us further, check the links in the description. Thanks for watching, and I'll see you in the next one.